This is the second part of looking at how to implement arithmetic circuits, and in particular addition and subtraction in Verilog. We are going to look at the generate capability in Verilog in order to make parametrized adders and subtractors, and we will also look at using directly arithmetic statements in Verilog. Along the way, we will take a look at vectored signals, at how to combine several signals into a vectored signal by using the concatenation operator. And we will also look at number representation in Verilog. In the first part of those videos about arithmetic circuits in Verilog, we had been looking at a module that we call add sub 4. That was an adder subtractor for 4 bits. And there we instantiated 4 copies of a 1-bit full adder subtractor module in order to make the 4-bit ripple carry adder/subtractor. Now, in Verilog, there is a construct which is called the generate block. Okay, so that's this one here, generate block, that can be used to specify as many adders as we would like to, as many 1-bit modules that we would like to, and mechanize that instantiation of those, of as many units as we need. Okay, it is in some sense similar to the for loop construction, but it's a kind of a special for loop that is just meant to be running inside of a generate block. Okay, so we will look also here at the for loop, and that will be used to instantiate the 1-bit add subtract module n times. Okay, if a for loop is included in the generate block, then the loop index variable has to be of the type genvar, which is a generate variable. And what that means in essence is that it has to be a positive integer. Other things can be done within the generate block. You can use if, else, or case statements, but here we are just looking at making a for loop inside that generate block. One of the things that has to be done is that we have to have some sort of naming for all those modules that are going to be instantiated, and the name of each module has to be unique. So we have to let the compiler generate numbers in the for loop that will give us unique instance names produced by the compiler, and that is done by adding a loop, adding a label to the for loop. So here's what that looks like. So this is for an n-bit adder subtractor which is parametrized. So we have here the setting for the parameter n. We set it to 32 for this particular example. And we're going to use the generate capability here. So down here is that generate keyword, and then it needs to be ended by an end generate. So this whole thing is the generate block. And that's where we will generate those different instantiations of the 1-bit full adder subtractor module. The beginning here of the module is just the same as it has been for other modules. We give it the name add sub underbar n because we can do this for an n-bit adder subtractor. Then there is the subtract add control variable here, and just to remind us again, so sub is going to be equal to 1 for subtract, and it's going to be 0 for add. And if we do use this module as a subtractor, the cin has to be set equal to 1, because the subtract itself just makes the 1's complement of the y input, and in order to make a 2's complement, we have to add in a carry into the adder, so cin has to be set to 1 if we set sub equal to 1. Then x, y are the two inputs, the two numbers that we want to either add or subtract, S is the sum, C out is the carry output from the most significant stage, and overflow is an indication that during the computation an overflow occurred if either two positive numbers are added together and the range of numbers is exceeded, or two negative numbers are added together and the range of numbers is exceeded. Then there are the definitions here for input. So sub and cin are 1-bit inputs, then x and y are n-bit inputs. The output s is an n-bit output, so here we have n bits. And C out and overflow, those are 1-bit outputs. And then we use an internal vector of wires, and that is going to have n plus 1 wires, so n plus 1 bits. And that's just used for the carry, to ripple the carry between the different stages. And the reason why we make it n plus 1 is so that we can include the carry input and the carry output in this array. That just makes for a little bit nicer programming or actually generating of the modules. Okay, then we have here the gen var. We happen to call this I. So this is the generator, the generate variable. That's this number that will have to be a number that's greater or equal to 0. And then we make a few continuous assignments here. Cin, that the first C0, the first bit in that internal vector for carries, is going to be set to Cin, and the last bit of this one, Cn, is set to C out. So that just takes care of the carry input and the carry output into that ripple adder. And the overflow is, as usual, the XOR of the second last and the last carry in the computation. Then we get to the generate stage. So we generate here for I equal to 0 as a starting condition, I being less than n being the ending condition, and I equal to I plus 1. So that's the increment that we're making every time. And we just have actually one generate statement here, so we don't have to have a begin and an end statement. And in fact, we don't need that for the generate anyways, because we have to generate and end generate. But then for the for loop, we do need the keyword begin and the colon here, because we have to be able to give the compiler a chance to name all those instantiations, to give them unique names. And the way this is being done with that label here, so this is the for loop label. Okay, so the way this is done is that the compiler, when it runs this for I equal to 0, it calls this stage 0. And then when I is equal to 1, it calls it stage 1, and so forth, in the same way like we are making vectors of signals. So here are the names that are going to be used for those, or that are going to be produced for those different instantiations of that 1-bit full adder subtractor. So it will be stage, and then in brackets here 0, and then dot FAS. So the FAS is the part that is given here. And then stage 1 dot FAS up to stage n sub n minus 1 dot FAS. And the way we specify here the connections of the inputs and outputs of those stages is pretty much the same as we would if we had instantiated all those copies by hand, except that it's now indexed with the index I. So SUB, the subtract control, that's going to be common to all of those adder 1-bit adder modules. Then there is the carry input CI, there is the carry output CI plus 1, and those go into that intermediate vector here of carries. And then we have XI and YI, those are the ice bits of the two inputs that we are going to add together or subtract from each other. And then we also have Si, that's the ice bit that is going to go into the sum that eventually forms the n-bit sum at the output. And then we're done with that main module, and the generate statement will just make now n copies of this full add sub module, this 1-bit module, through that for loop, through the conditions of the for loop that are given here. And then, of course, we need to specify that full add sub piece, that sub module, and we can do that in the same file, or we could have produced a separate source file. Either way works. Here we chose to do it into the put it into the same source file, and we have here the behavioral description again of the 1-bit full adder / subtractor. So here the W, that is the ones complement of Y. For the case when we are using this as a subtractor, then we have the sum of X, or the XOR actually, which creates a sum bit of X, W, that ones complement, and carry input. And the carry output is computed as the majority decision on X and W, or X and C in, or W and C in. So one thing to notice here is that we actually have been using continuous assignments throughout both of those modules. The generate, which instantiates modules, the outputs of that go into wires, because those form permanent connections. Those are not procedural statements. And so we have, for our inputs and outputs, we have actually all wire signals. So none of those here, which we had declared at the beginning, or the intermediate ones, are actually of the register type. But what we want to explore now a little bit is what exactly is that definition, distinction between nets and variables in Verilog. That's something that frequently leads to confusion when Verilog code is written and then does not get compiled because of a mismatch between outputs from certain entities and those outputs going either to nets or variables when they should go to the other thing. So a net in Verilog represents a node in a circuit. Nets can be of different types, but for the purposes that we are using it for synthesis, the most important nets are of the wire type. And wires connect outputs of logic elements to inputs of other logic elements. For example, an output of an AND gate going to an input of an OR gate, that would be such a wire. Or an output of an instantiated module that is being connected to something else, that would also be of the wire type. Undeclared signals in Verilog default to the scalar wire type. And if there is a vector signal of the wire type, then it has to be declared explicitly, for example, as is shown here. Okay, so if we would just have used a single bit for the carry, then we could just have simply have written C, or actually just simply used C without declaring it beforehand. And the compiler would assume that it's a wire type signal which has just one bit. Now variables are provided in Verilog to allow a circuit to be described using procedural assignments. That considerably extends the flexibility in specifying things, because we can use such things like an if-else command, or we can use for loops, we can use case statements, and so forth. There are two types of variables. One is of type reg, which stands for register, and the other one of type integer. For example, a for loop, the the loop variable, that has to be of type integer. And now the rules that generally apply for knowing what type to use when interconnecting things are as follows. You use the net type, in our case mostly the wire, for signals that are driven by a module output, by a primitive output. A primitive is something like an AND gate, an OR gate, a NOT gate, and so forth, or by a continuous assignment, which are the assignments of the type assign f equal to, and then some Boolean expression, for example. And variable type we use, which could be register or integer type, we use for signals that are assigned a value in a Verilog procedure. Okay, and a Verilog procedure, the most frequent one that we're going to use is the always block. That is one of those Verilog procedures whose output needs to go into a variable of type register in most cases, because the Verilog procedures are just carried out whenever some signal changes, but then the output of that needs to be stored somewhere because they are not assigned as a direct connection from one logic block to another. So far, when we have been specifying our adders, we have been doing that by actually using XOR sums or by using majority logic or the majority decision function for the carryout. More or less, we have been using Boolean expressions in order to specify what an adder is supposed to do, or in some cases even we used structural descriptions in terms of directly AND and OR and XOR gates. Another way to do things is to actually use arithmetic statements in Verilog. And if we assume that we have vectors x, y, and s defined as is shown here, so we have n-bit inputs x and y, we have an n-bit output s, then we can actually use the arithmetic statement s is equal to x plus y. Now keep in mind that in Verilog, what we have been often using a plus for when we use AND, that's represented as the ampersand, and the OR is just a vertical bar. So the plus here is actually an arithmetic plus. And in fact, we could also have used x minus y. So we could actually have made this a subtraction rather than an addition if we would have wanted to. So this expression here represents an n-bit adder, and the Verilog knows that it's going to be an n-bit adder because we have specified the inputs and the outputs as being n-bit quantities. We could actually have made it such that one of the inputs has, let's say, n minus 5 bits, and the other one has n minus 1 bits, and then Verilog would pad on the left with zeros in order to make both of the vectors of length n minus 1 if n minus 1 is the maximum, or actually length n if index n minus 1 is the maximum index. So that's how it knows how many bits have to go into that adder. One of the disadvantages of using an arithmetic statement is that we do not get access directly to the carry out signal, for example. So what if we want C out, or if we want to have Cn and Cn minus 1 in order to detect overflow? This does not give us an indication whether overflow has occurred or not. So in order to incorporate some of those things, we can use several little tricks to reconstruct those numbers that we need, or to produce them in the first place. So in order to get the carry out, Cn plus 1, actually a Cn, which requires n plus 1 bits, we can trick Verilog into believing that we're actually doing an n+1 bit addition. And we do this by taking our vector x that has n bits. Okay, so we have n bits on this one. But we concatenate that with another bit, which has been specified here as 1 apostrophe b0. So that means just a single 0. So what we get is we pad x on the side of the most significant bit. We pad that with a 0 and then have x. And so now we have n+1 bits. And the compiler now will generate a sum at the output that also has n+1 bits. And we also pad the y with a 0 here. Again, the format here is 1 apostrophe b0. That means 1 bit, and b means binary, and 0. So now we have n+1 bits for y, and the most significant bit has been set to 0. So adding those two bits together will never give us anything non-zero. And so the only way we can get something non-zero out is if the carryout actually has to be 0. If the previous stages were such that we had 2 1s or 3 1s to add together, then we get the carryout. So in this way, we obtain the carryout as the n+1st bit in this summation. And the operator here that we have been using, the curly brackets, this one here, that is called the concatenate operator because it allows us to take several bits or vectors together and make larger vectors. So we could, for example, concatenate two 8-bit quantities and make a 16-bit quantity by using this concatenation operator. So if A, for example, has m bits and B has n bits, then the concatenation of A, comma B gives an m plus n bit vector with the bits from A being the most significant bits and the ones from B being the least significant ones. So now we're getting to the code for an n-bit adder subtractor that uses just arithmetic statements. You can see this is the whole description here that we are seeing. You can see that this is actually considerably simpler than what we have been doing before. And we have again, the module keyword here, the add sub n is the name of the module, and then the subtract control as an input, the carry in as an input, x, y, and s as n-bit quantities, and then C out and overflow as 1-bit outputs. So we have the usual description here of our input-output things and the parameter n equal to 32, so that we can set this to whatever number we would like to. We have n-bit quantities here. Okay, so n bits. Then we have some internal quantity w that's being used for the ones complement when we do subtraction. So this is ones complement. Okay, so here it is actually shown. We assign w to be the XOR with SUB, the subtract control, and y. Now here is an interesting construction. We have here an n and then a curly bracket SUB, like this. Okay, the reason why we have that here is that y is an n-bit quantity, but SUB is a 1-bit quantity. So if we would just be doing SUB XOR with y, that only XORs bit 0. XORs bit 0 of y and produces a 1-bit. It actually does produce an n-bit output, if I do remember that right. But the SUB is only going to be the least significant bit in here. Everything else gets padded with 0. And so if we pad with 0 in an XOR, 0 XOR with x, that actually gives us x back. Okay, so because if you have 0 XOR with 0, that gives us a 0. If you have 0 XOR with 1, that gives us a 1. So only the least significant bit would get inverted when we go into subtract mode, and SUB is equal to 1, unless we use this construct. So this construct, what it does, it makes a concatenation of SUB, comma SUB, etc., SUB n times. And then we put that here into a concatenation operator. So we have to put the concatenation around it in order to actually make that SUB, comma SUB, and so forth. And then we can XOR that with y. This is going to be a component-wise XOR of all the n bits. So in this way, we get the ones complement if SUB is equal to 1, and that allows us then to compute the 2's complement by making the carry-in function equal to 1. Then we compute the sum, as we just outlined on the previous slide. We trick Verilog into thinking this is an n plus 1 bit number by adding the 1 apostrophe b0 and to x and to w. And then the output is going to be n plus 1 bits, because s is only n bits. We get an additional bit that we put into C out, so that's our carry out. And then in the end, we have to compute overflow, and the way we do this is we recreate the carry bit C sub n minus 1 by this computation here. Okay, so this is equal to C of n minus 1. And then we XOR that with carry out, which is Cn, and in this way we get the overflow condition taken care of. This whole block here, or this whole module, is a behavioral description with continuous assignments. We did not have to use any procedural block like an always statement, even though we could have put this into a procedural block if we would have wanted to, but then we would have made the W and the S and the C out and the overflow would have to be of type register if we had put this inside of a procedural block, but we have not done so here. So here is the explanation of how we get that C sub n minus 1 and then the overflow condition. We know that the n minus the bit with n minus 1 index in the sum is the XOR of xn minus 1 and wn minus 1, cn minus 1. And so we can turn this around. We can add in or XOR in cn minus 1 on both sides and also sn minus 1 on both sides, and then we obtain that C sub n minus 1 is equal to S sub n minus 1 XOR x sub n minus 1 XOR W sub n minus 1. So in this way we get the second most significant carry, or the second last carry, and then XORing this with the last carry just gives us this whole expression here. And that's the expression that we used to indicate whether overflow occurred or not. Now we were trying as much as we could to actually parametrize those implementations of those adders to make them n-bit adders with just a parameter statement. And we have been generally setting this to n equal to 32. But if you would like to instantiate one of those adders with 16 bits or with 8 bits, then we would like to have a mechanism by which we can change that n, that parameter n, easily. So here we suppose that we have to compute the sum s equal to x plus y plus c, consisting of 3 numbers, and we assume that x and y are 8-bit numbers, and c is a 12-bit number. Of course, we could use a 12-bit adder 2 times in a row in order to compute the result, but it's kind of more elegant and requires potentially less hardware if we actually tailor this to the known word sizes here. So adding two 8-bit quantities together, we are going to, if we do not want to produce overflow, we are going to get at most 9 bits, so we can use a 9-bit adder for that, and then we can add this 9-bit number to the 12-bit number. And if you want, again, not to produce overflow, then we would get a 13-bit number as a result, so we would use a 13-bit adder. So here's how we could write that by using instances of the add sub n module. So this is the adder subtractor for n bits with that parameter n equal to 32 in those modules that we have been writing so far. So we would start out with the module keyword, then give that whole thing a name. So I called it here x, y, z add. And then we have our three inputs, x, y, and z, and the output s. So we declare all of those. So we assume that x and y are 8-bit inputs. So here we have 8 bits. Then z, we assume, is a 12-bit input. And the output, we assume, is going to be a 13-bit quantity, because we do not want to generate overflow and worry about overflow here. We will compute some intermediate sum S1 that will have 9 bits. That will be the sum of the two 8-bit numbers. And then we also create some wires for cout and overflow, because the adder modules that we are going to use create the cout and overflow. We're not going to use that in this module, but we're just providing a place here where those variables can, or where those results can go. It's actually not variables because this is a wire. Those are net names. So now we make a first instantiation of the add sub n adder subtractor for n bits. We call it u1. And we put 1 apostrophe b0 for the first two quantities. So this would indicate whether it's a subtract or add. So we set this to add. And then the second one, that's the carry in. We're setting this to 0. And then comes x and y, those two 8-bit numbers. The intermediate sum here, which is going to be a 9-bit number, and the cout and overflow that we don't use. So here we would now like to specify that we are using a 9-bit adder rather than a 32-bit adder. And we can do this by this statement here. We can redefine that parameter. So by saying def param u1, that's the instance name here, dot n. So that's the n, that variable n that's being used in the add sub n module, and we set that equal to 9. So that overrides the n equal to 32 in the module u1. And we're actually producing just a 9-bit adder rather than a 32-bit adder. And then we do the same thing. We call that add sub n, or we instantiate that add sub n again. This time we call it u2. We put in the same kind of inputs here, except that we don't have an x now. We put that intermediate sum s1. And instead of y, we're adding the number z. That's the 12-bit number in. And then we produce the output sum s. That's the 13-bit quantity. So now we want to instantiate a 13-bit adder. And we do this by the statement here, def param u2.n equal to 13. Okay, so that overrides again the n equal to 32 in the add sub n module. There is an alternative way how this can be done. We could also have written add sub n and then the pound sign that stands here for parameter, and then just write 13. What that does is it picks the first parameter that it encounters in the add sub n module and sets that equal to 13. Since we have had only one, that's just going to be that n parameter. And then we write the rest of it the same. We have the instantiation name u2 and the inputs and the outputs of that particular instantiation of the add sub n module. We have been using numbers of the form 1, b0 in order to pad some of our quantities with a 0, or to just simply set a binary 0, for example, for the add subtract control. And the more general case of specifying numbers actually goes along the lines of this specification here. Numbers in Verilog can be given as binary, b, octal, little o, decimal, d, or hexadecimal, h. And the size of those numbers can be either fixed or unspecified. If we have sized numbers where we want to tell precisely how many bits the numbers can use, then the format is this one here. We specify the size in bits, then comes an apostrophe, then comes the radix identifier, and then comes the actual number in terms of the significant digits of the number. If we specify fewer digits here than we gave the size in bits, Verilog will automatically pad the numbers with 0 on the left. So here's an example. The decimal number 605 could be represented using 10 bits as follows. Remember, 9 bits can go up to 512. So 9 bits are not enough for that number. 10 bits can go up to 1023. So this fits into a 10-bit number. So we could write it as 10 for the length of the number in bits. The length is always in bits in the size specification, even if the radix that we use is different. Then b here for bits, and then 10010 triple 101. So that happens to be 605 in binary. Then we could specify it as 10 apostrophe, the little o here, 1135. If we parse this number here, 3 here, 3 here, 3 here, and then this one here with padded is 1, we get the 5, a 3, a 1, and another 1, so that's the 5311. That's the octal representation. The decimal representation, 10 apostrophe d 605, and the hexadecimal representation, so we would now group this in groups of 4 bits, like this, and pad with zeros on the left. So with the last one here, that is 13, that is d in hexadecimal, then comes 5 and 2. So hexadecimal 25d specifies the same number. Any of those can be used to specify a particular number. It depends on what is most convenient, or sometimes what is the most self-explanatory when we write Verilog code. If we have unsized numbers, then we just simply leave out the size specification here before the apostrophe, and we would just write apostrophe b and then whatever the binary digits are, and Verilog will determine how many bits to use. Typically that would be the word size of the computer that it's running on, something like maybe 32 bits, in some cases maybe 16 bits. And if we have an octal number, we would do the same thing, apostrophe octal, and then 1135 for the number that we had above. For a decimal number, we actually do not have to specify the apostrophe d. In this case, we can just write 605, and the compiler will interpret that as a decimal number. And then the hexadecimal number is the apostrophe h25d, as we had before. Negative numbers in 2's complement are represented using a minus sign in front. So if we wanted to make a -3, for example, we could just simply write -3 in decimal, or we could write minus, let's say we wanted to make this a 4-bit number. So we would then write this as -4 and then the B, and then 0, 0, 1, say. And so it would make this into a 4-bit 2's complement number, so that would become then 1, 0, 1, 1 stored internally.